Hello students, this is Mr. Allen, and today we are going to move on to Chapter 7. Chapter 7 is on similar figures, and we are going to look today at Section 7.1 and 7.2. 7.1 is on proportions, and 7.2 is on similar figures. So our objective here is to be able to write ratios and solve proportions. That's going to be for Section 7.1. And in Section 7.2, we want to be able to identify and apply similar polygons. So let's focus first on Section 7.1, which is on ratios and proportions. And let's go ahead and start off here. I'll move my picture down a little bit. Start off here by looking at some model airplanes there. These are drawn to, or these are models have a certain scale factor. We call that like a ratio. So a ratio is just a comparison of two quantities. So for example, this first jet fighter here, this model jet fighter, is 1/32. That means 1 to 32. In other words, 1 inch is equivalent to 32 inches in the actual airplane. So if something on the model measured, let's say, 1 inch, then in the actual aircraft itself, that would be 32 inches. There's also something called an extended ratio, and that's when you're just comparing three or more numbers. So an example of that might be A is to B is to C. And we'll see an example of that here in a few slides. So let's look at our first example here. So I have a bonsai cypress tree shown here on the right, and this is a small version of the full-size tree. So this particular tree and this model is 1 foot by 15 inches. So obviously the real tree is a lot taller than that. In Longwood, Florida, a bald cypress tree called the Senator stands 118 feet tall. What is the ratio of the heights of the Senator? Okay, so a ratio, as we just saw, compares two quantities. So what we want to do is we want to compare, let's say, the model's height, I'll call it model, to the actual height of the actual tree. So in this case, the model height, well, we can clearly see that that's 15 inches. In fact, I'll put the notes here, it's 15. 2 marks there, that means inches. And then the actual height of the tree, well, it says it's 118 feet. I'm going to kind of draw this in a different color because this is actually not how we want to leave our answer. Feet would just be 1 mark like that. And so what we want to do is we want to make sure if we're going to have a ratio, we want them to be the same units. So it's going to be 15 inches to, and so what I need to do is convert this 118 feet to inches. So what you're going to do is you're just going to take your calculator and you're going to do 118 times 12. And that's going to give us 1416. So this is the ratio. And you know, there's one other thing I should probably double check here. In general, you want ratios to be completely simplified. Yeah. So this actually isn't the best answer. So the best answer is 5 to 472. And this is the answer that is completely reduced. So in general, we like to make our ratios completely reduced. So this is true, that's true, but this is the best answer. So it's 5 inches to 472. So 5 inches in this tree here would represent 472 inches in the actual tree. All right, example 2. It says the lengths of the sides of a triangle are in the extended ratio. So I mentioned extended ratio earlier, so we're going to see an example here. It says the perimeter of the triangle is 120 centimeters. What is the length of the longest side? Well, the good news is I've already got my picture drawn here. There it is. So we can see that the ratios, this extended ratios are 3 to 4 to 5. Now, I don't know what n is because remember this ratio, this is an extended ratio, but the ratio is reduced. So if you took 3 plus 4 plus 5, you do not get 120. So what we're going to do is we're just going to throw a variable in with that. So we could say that 3n plus 4n plus 5n equals 120. And so now we can solve this. So that'd be 7, that'd be 12n equals 120, and that's easy. If we divide both sides by 12, we get 10. So n is 10. That's nice, but that's not the question that's asked. The question is, what's the length of the longest side? So we need to take that times 5. So 5n, which is the longest side, means we got to do 5 times 10. So it is 50 centimeters. That is the longest side, and that's our final answer for there. So that was an example of an extended ratio being used. Now, the big idea really for this section, I mean, ratios are important, but we want to get to this thing called a proportion. And I probably should have put a slide in here, but I didn't. Let me go ahead and maybe write that right here. A proportion is just two equal ratios. You're probably familiar with this. You studied this in Algebra 1. So two equal ratios. For example, this is a proportion. We read that A is to B as C is to D. Here's another example of a proportion. 2 is to 3 is 4 is to 6. So, by the way, the red terms A and D, these are what we call the extremes, and then the blue things are called the means. Not going to worry too much about that. But the big idea is this: if you want to actually solve a proportion, we are going to use this cross product property. And when I used to teach middle school math, I'd have my students draw these little things here. So you would do the 2 times the 6, so that's the product of the extremes, time equals the product of the means. So in that case, 12 equals 12. Let's see an example, and I think you'll feel more familiar with this. So I'm hoping that you guys remember something like this from Algebra 1. So it says, what is the solution for each proportion? So what we're going to do is we're going to use this last property, which is the cross product property. So we're going to cross multiply here. So we're going to take 5 times x is equal to 6 times 4. So 5x is equal, oops, that doesn't really look like a 5. Let me fix that. So 5x is equal to 24. So x is equal to, and now I'm going to go ahead and use my calculator because this is going to give me a decimal answer. And we're going to take 24 divided by 5, and we get 4.8. And we can even check that answer by just putting that 4.8 in there and checking, does 5 times 4, does 5 times 4.8 equal 6 times 4? Well, when I take 5 times 4.8, I get 24, and 6 times 4 is also 24. So that's a check. So we cross multiply here. We cross multiply. All right. Now, the second one's going to be a little bit more work because I've put a little bit of algebra in there, more algebra than the first one. So again, we're going to cross multiply. So we're going to cross multiply here. So we're going to have 3 times y plus 4 equals 9 times y. So now I want to use, I could use the distributive property. There's other ways I could do this, but let's go ahead and distribute the distributive property here. So we're going to get 3y plus 3 times 4, which is 12, equals 9y. Now I'm going to minus 3y from both sides. So when I take 9y minus 3y, I get 6y. And clearly, you can see that y is going to be equal to 2 when you divide both sides by 6. So y is 2. And again, we could check that. If, in fact, let me do this one a little bit more deliberately. If I put a 2 in here, because that's what we got for y is 2, you're going to get 6 over 9 equals 2 over 3. And clearly you can see that 6 times 3 is 18 and 9 times 2 is also 18. So we're good to go. So this is probably the slide that you're probably most comfortable with because you did a lot of this in Algebra 1. All right, so let's move on to section 7.2. This is where we get into the geometry of things, and everything back in 7.1 is just to kind of get us geared up for here. So these are similar figures, these two triangles here, and I just grabbed this image off of mathbits.com. But so this is how we would write symbolically that this triangle ABC is similar. So we use this tilde symbol to represent cylinder. So what is similar? Similar figures have the same shape, but not necessarily the same size. They can be the same size. So congruent figures are similar, but most of the time when we do problems involving them, they are not the same size. So here we can see that we have this quadrilateral here. I'll call this quadrilateral 1, and this over here is quadrilateral 2. It turns out that those two quadrilaterals are similar. So they are the same shape, even though one's kind of rotated. But they are not the same size. And we'll use something called the scale factor, which we saw earlier when we talked about that model airplane back in section 7.1. So here's a little bit more formal definition. Two polygons are similar if corresponding angles are congruent and the lengths of the corresponding sides are proportional. So this is really the big idea. Let me highlight the important parts. The corresponding angles are congruent. That's important. And it's also important that the lengths of the corresponding sides are proportional. This is probably the most important slide in all of this presentation. In fact, it's probably the most important slide in this entire chapter, and it is the definition of similar polygons. So if I said that this trapezoid here, ABCD, was similar to trapezoid GHIJ, then I'm saying all of their corresponding angles are congruent and all of their corresponding sides are proportional. So most students can kind of pair up, angle B goes with angle H and angle C goes with angle I, and they're congruent. Most people get that. The important piece, though, is you need to get these lengths paired together. Okay. So what I'm talking about is, this side here, this is side AD and side GJ. So we're kind of using the same thing we did with congruent figures, but you'll see that right here, here's that AD and GJ. So I think it might be a little bit easier to actually explain this a little bit more with an example. So let's look at this example here. I have two triangles. It tells us that they are congruent. I'm sorry, that they are similar. Let me make sure I make a point of that. I just messed that up, and I could maybe see you doing the same. Remember, just the tilde, no equal sign. This means they're similar. So it first says, what's the congruent angle? So now I got to be careful. Now I'm going to use the correspondence. You see how M comes first in this first triangle? So there's M, and it's paired up with the first letter of the second one, which is S. So that means that those two guys have to be congruent. So the measure of angle M has to be congruent to the measure of angle S. The second letter in the first part is N, and I'll put 2 marks there. And that's got to be paired with the second angle of the second triangle, so that's R, so that's got to be this one here. So that means that angle N is congruent to angle S. Oops, not angle S, angle R. I did that wrong. Angle R. Let's fix that. And finally, obviously, you're going to have that angle P, the leftover angle, is congruent to angle T. So this first piece, the congruent angles, is based on the fact that the definition of similar polygons is that the corresponding angles have to be congruent. So those were the corresponding angles, and therefore they have to be congruent to one another. Now the corresponding sides, and we play basically the same game, and I'm going to erase all these markings for now, but let me just go ahead and get this started. So side MN, that's this side here. That's the first 2 letters of the first triangle. So that has to be paired up with the first 2 letters of the second triangle. So this is SR. So you're going to write MN, that length. Notice I said length is paired with the length of SR. The second one, and I'm going to do NP. So NP, that'd be this length, and then it has to be corresponding to RT. So I'm going to write NP proportional to RT. And then, of course, you're going to have the last one, which is going to be PN. PM is going to be proportional to TS. And so that's that remaining. And you know what? I am not doing a very good job here, guys. I'm so sorry. These are not congruent. They could be congruent, but they're not in this example. So the key here is notice that here we have congruence, here we have proportional. Proportional, there we go, if I can spell. And this is called an extended proportion, just like we had an extended ratio, because there's 3 of those. Okay, so again, this is going back to this definition. The corresponding angles have to be congruent and the lengths of the corresponding sides have to be proportional. So the mistake I made when I was marking these, this segment here is not congruent to that segment in this example. Let's look at a better example. So here we've got 2 trapezoids. Can you see them? They're kind of overlapping. You kind of have this, and let me highlight this a little bit. You kind of have this smaller trapezoid. Let's do it in yellow. We kind of have the smaller yellow trapezoid here, right? But then you have the larger trapezoid A, B, C, D. And again, in this problem, they're telling us that those 2 trapezoids are similar, so they are the same shape, but in this case, they are not the same size, and they're asking us to find the value of x. Now, the value of x in this example is not involving an angle, so we don't need to deal with the corresponding congruent angles. What we do need to do is we're going to write an extended proportion. So what I'm going to do is this. We know that AB has to be proportional to EF because of the congruent statement. The first 2 letters of the first one, the first 2 letters of the second one. That has to be equal to then BC over FG. So that was the second and the third, and the second and the third. So let's do the third and the fourth. So that's going to be CD, and the third and the fourth is GD. And then last but not least is the last and the first, so that's going to be DA. And then finally DE over here. So those are all of the corresponding sides, and I'm just using my congruency. You could also look at the picture. Look, here's AB, that's this side here. And it is going to be proportional to this corresponding side, EF. So AB is to EF. That makes sense. Okay. BC, that's, where's BC? That's this side over here. I'll do it maybe in a different color. Let's do purple. That's this side here. It is proportional to this. So now what I can do is I can simply write in all the things that I know. So that I know that AB is 5. I know that EF is Y. I know that BC is 7.5, and I know that GF is X. I know that CD, that's this guy, where's CD at? Oh, it's this big long side. I don't know what CD is, so I just got to write CD by itself because I don't know what it is. And do we know what GD? Nope, we don't know what GD is either, so that doesn't really help me anything. But what about DA? Well, the length of DA here looks like it's 9 according to the picture, and ED looks like it's 6. Now I have everything that I want to know. In this problem, I'm only asking for X. So since I'm only asking for X, I only need to compare this to this. In other words, 7.5 is to X as 9 is to 6. And now I'm going to cross multiply here, and I'm going to use my calculator. So 9x is, and now I'm going to do 7.5 times 6. And I get 45. Oh, that's great. Now, x in this case is going to be what 45 is divided by 9, which is 5. So x turns out to be 5. So now my question, and I'm not going to answer this question, I'm going to ask you, is what would y be? What would y be? How would you find y? All right, last example here. Actually, I think there might be one more after this, and I hope we're not going too long on time here. I think we are going a little bit long. So let's do this one, and then I think I had one. Yeah, I need to do the last one too. So guys, I'm sorry, this is going to be kind of a long video. So they're asking us, is this polygon, in this case a quadrilateral, similar to this polygon? So let's just look at that. Remember, if they're similar, then we need to figure out if they have the property that all their corresponding angles are congruent, which if you just look here at this picture, you can see that all the angles are congruent. So that's a good sign. But we also need to compare all their corresponding sides. So let's check here. So let's compare this side here, which is MJ, 6, which would go to WT. So 6 is to 6. Well, that looks encouraging. And then this side here, which is 12. Okay, I can pretty much stop right now. Would you say that this is a true proportion? I would say heck no, right? Because when you cross multiply there, you're going to get 36 equals whatever 12 times 6 is, which is 72. And those clearly do not equal each other. Therefore, there is no way these are not similar. They cannot be similar. Let's go ahead and check B now. So do we have corresponding angles? Yes. Now be careful. On this one, it's a little bit different. So we've got things kind of flipped upside down. So you see how angle A goes with angle D and angle C goes with angle F? All right. So first of all, that all angles are congruent. So, right. So let's go ahead and write that down. All angles, let me be more specific. All corresponding angles are congruent. So that's good. Now I need to again check their corresponding sides. And this will be a little bit easier on this one because the sides are, there's only 3 of them and I can order them no problem. So the shortest side of the first one is 8. Does that go with the shortest side of the other side? So that's 10. And then the next longest side is 12 in the first triangle and 15 in the second. And then the last one is going to be 16 is to 20. Now here's the question. If I reduce all of those fractions, and I can do that with my calculator if I wanted to, I could do 8 divided by 10, which turns out to be 4/5. So that's good. What about 12 divided by 15? Well, let's see here. 12 divided by 15. I'm going to convert to, oh, that's 4/5. So that's 4/5. What about 16 divided by 20? Oh, that's 4/5 too. So in other words, all of those are the same ratio of 4/5, and we know that all the corresponding angles are congruent. Therefore, we can conclude that triangle ABC is similar to triangle. Okay, so I got ABC. So I went from double to triple. So I'm going to go from double to triple. So that's going to be DEF. And so that's our answer. So this one was a yes. They are similar. Okay, last example, we'll wind this down. All right. So we've got a picture here. This is a scale drawing of the Golden Gate Bridge in San Francisco. The distance between the 2 towers is the main span. So we're talking about this distance right here to, oops, let me do that in a different color here. Let's do that in, let's do that in red. So we're talking about this distance to this distance. That's called the main span. What is the actual length of the main span? Now they give us the scale. And so what we would have to do in a problem like this is you got to actually get out your ruler and you got to measure it. Now, guys, I'm just going to pretend that I'm measuring it, but I'm going to kind of make it an easy number, and I'm just going to kind of eyeball this. And it looks like, actually, it almost looks perfectly that it's 6 centimeters. So in the drawing, it's 6 centimeters, right? So the actual length, I don't know what that is. So I'm going to put X meters. But I know that the scale, and I'm going to now use the scale, which I'll write in black, is 1 centimeter to 200 meters. So this is what we call a proportion. So now, in order to find my answer, I can just cross multiply. So let's go ahead and finish this up. I'll do that in green. So I'm going to take 6 times, in fact, I'll show my work. It's going to be 1 times X equals 6 times 200. So X is going to be 1200. In other words, the main span is roughly 1200 meters. That'd be our final answer here. Now, guys, I'm going to just let you know, I'm being honest. If you check the main span of the Golden Gate Bridge, it probably isn't exactly 1200. I just kind of used my computer and this ruler to check that. That's just the way it came out in this. We could, in fact, maybe you want to Google that and tell me I'm wrong, and that's fine. So, all right, we're going to end the presentation there. Thank you guys so much for your time.